In this section and the next section, we will discuss algebraic properties of matrices. Now, it is customary to use capital letters to name matrices. So, for example, I could have a matrix A written in this form, A, B, C, D. So that would be the capitalized, again, capital A to name the matrix. And of course, X, Y, Z's, whatever the letter, doesn't matter. It's not material. But we use capital letters to name matrices, and we use subscript notation to actually show the elements or label the elements of the matrix. So for instance, in general, suppose I have a matrix that looks like so. The element in the first row, first column is going to be A11. Second row, first column, and so on, all the way to, let's say this matrix has m rows, so that's going to be m1. The element in the first row, second column, first row, third, and dot dot dot, so forth and so on, all the way to a subscript, that is a sub 1n. So this matrix clearly has m rows and n columns. The element in the second row, second column, second, third, and so forth. Second row n is the last one in that row. So we can pretty much list them like so. In the last row, a sub m1, I have a sub m2, mth row, second column, and then I have a sub m3, and I have a sub mn. Okay, so that's just the notation for subscripts, are the notations for the elements of the matrix. Now remember, every matrix has a size, order, or dimension. This one is an m by n matrix, meaning m rows, always rows followed by columns. So this one, columns will be n, rows by columns. So the order or size or dimension of this matrix is going to be m by n. Now, in terms of the algebra or algebraic property of matrices, we're interested in basic operation: addition, subtraction, multiplication, and division. Now, division, first of all, is not defined with matrices. We do not have matrix division, but we do have matrix addition, subtraction, and multiplication, and they're not always defined depending on the size or the order of the matrix. Okay. Now, matrix equality, by the way, let's say I have matrix A is equal to 1, 2, 3, 4, and matrix B is going to be 1, 2, 3, 4. So these two matrices will be equal. Two matrices are equal if they have the same size or dimension, and every element in the corresponding position are the same or equal. So if I have another matrix, let's say C, so let me just say that A is equal to B in this one. So suppose I have another matrix C in this one, I'm going to make it 1, 2, 3. Actually, let me switch to 4 and 3. I was going to change 4, but rather, there we go. I switched the position of 3 and 4. Now, just because they have the same elements doesn't mean that they have and that they're equal in this case. So we say A does not equal to C. And the reason, again, although they have 3, but see, 3 is not in the same position. Corresponding to that position is a 4, which are not the same. All right. So everything, in other words, they have to be a carbon copy, an exact image of the other one. All right. Now, matrix addition. We can add matrices. To add two matrices of the same dimension, they gotta have the same dimension, same size. And let's check out the operation addition of matrices. So they have to have the same dimension, and to do this, you add corresponding elements. Okay, and remember, only matrices of the same dimension can be added. All right, so for example, matrix addition is easier to show with numbers rather than symbolic representation. 6, -9, 2, and the other one is, let's say, 4, 1, 3. And if I'm adding this to, so remember the dimension of this one is going to be 2 by 3. And let's see. So I need to create another 2 by 3, correct? They have to have the same size. And suppose this is 6, negative 3, 4, something like that. This is also 2 rows, 3 columns. So as long as they're identical, the dimensions are exactly the same, then we can add corresponding elements in that same exact position. So 6 adds with a negative 8, so I have negative 2, negative 7, 5, 10, and what's next? 1 and negative 3, negative 2, 3 and 4 makes 7, and there you have it. Simple, very simple to add them. And subtraction, we can also we'll define subtraction as addition with opposites. Let's do one more addition just to make sure, because sometimes you may have expressions, not numbers, in a matrix. So this time I'm making up, let me move down lower, call it example. So let's say I have this matrix. I'm going to make it simple again, a 2 by 2. 3x plus y, negative 2y, x plus 2y, and then 3y. Ultimately, these become numbers in a matrix. Suppose I'm adding another matrix. It's got to be 2 by 2, right, to have the same dimension. And this one is 5x and x. Now, if I add corresponding elements in the same position, then I'm going to get 3x and 2x. That would be 5x plus y. And then the other one is just negative 2y, plus 3y is just y. Bottom, 5x and x makes 6x plus 2y. And the second row, second column element, 3y plus x, or x plus 3y, however you write it. And there we have this. Okay. Now, what if, let's say, what if I have a matrix? Let's do one more of the addition. Suppose I have a matrix that's x plus 2, y minus 6. Let's go z minus 3 and w plus 5. And then let's say that we want this to equal to another 2 by 2 matrix, negative 2, 8, 0, 3. All right, so how is this going to work? Well, because corresponding elements must be exactly the same, so we will do that. We, in fact, equate corresponding elements. So x plus 2 should be negative 2, from which we get x is negative 4. Y minus 6 should be 8, from which add 6 to both sides, we get 14. Z minus 3 would equal to 0, so that means z is 3, and finally w plus 5 is 3. So w must be, subtract 5, we get negative 2, and here we have the solution to the variables for this example. All right, again, this pretty easy, straightforward, nothing drastic. Now, we also, before we look at the subtraction here, just want to mention a few special matrices here. For example, if I have a square matrix, what is a square matrix? A square matrix, again, if m equals n, row and columns of a matrix are the same, then the matrix is a square. Okay, so rows and columns. So for example, I could have a matrix, a square of size n or order of n that looks like this, n by n square matrix. Or I could have a 3 by 3 matrix. I could have a 4 by 4, 2 by 2, and so on and so forth. So that would be a matrix. Each of these would be square matrices. Okay, now sometimes we come across we call the row matrix. So what is a row matrix? A row matrix is just that. It has just one row, a single row. So they call it a row matrix. It has just one row. So what is this going to look like? Well, in terms of listing the elements of a matrix, A12, A11, A12, A13, and so on, all the way to A1n. It has one row, but n columns. It's called a row matrix. Sometimes we may come across or work with column matrix. So what is a column matrix now? It is a matrix that has just one column. All right, and because it has just one column, I can go A11, A21, and so forth, all the way to AM1. So here's a matrix that has m rows, but a single column, one column. All right. Now, let's take a look at how we're going to subtract matrices. Okay, so we're looking at the matrix subtraction now. So to subtract a matrix, let's look at subtraction. And what is a subtraction? Well, suppose I want to subtract matrix B from A, provided again they have the same dimensions. Okay, so the operation can be done. So to subtract, we actually do addition with opposite of matrix. And because subtraction is not commutative, it makes a difference whether I do A minus B or B minus A. So let me say A minus B doesn't necessarily equal to B minus A. All right, unless we make them so that would work. But in general, it doesn't work. All right, so let's see how we're going to actually do a matrix subtraction. So for my example, I'm just going to choose a matrix A here. I'm going to make it to be 2 by 2, -5, 6, 2, 4. And matrix B, I'm going to let that one be another matrix, call it -3, 2, 5, -8. Now let's say we want to do A minus B. So to do A minus B, remember we're going to add opposite of matrix B to A. Well, what is opposite of matrix B? Well, let's write A first. A was -5, 6, 2, 4. We're going to add. Now, opposite of matrix B means every element of matrix B, you're going to change the sign on every number, every element in B. And there you go. That's going to be the opposite of all the elements, each and every element in that matrix. And then we can combine now these as addition. We add corresponding elements. -5, 3 makes -2. 2 -5 is -3. 4 and 8 makes 12. 6 -2 is 4. So this way, it's like we're adding all the time. Alrighty. Now, when it comes to matrix or matrices, anytime we multiply a matrix by a constant, so suppose in this example, I want to do 2 times A. Well, 2 times A, the constants that multiply by a matrix in matrix lingo or terminology, we call them scalars. So we're multiplying a constant 2 times A or scalar 2 times A. So keep in mind scalars are equivalent, or this symbol, the 3 line, means identical. Scalars are identical to constant. Scalars would be constants. So how do we do 2A? We just double up on everything. Okay, again, this is my A. I'm going to double up on every element. So that's going to be -10, 12, 4, and 8. Okay, it works the way you would expect it to work. Now, let's take a look at, since we introduced the idea of scalars, let's take a look at some scalar multiplications, operation with scalars. So for this one, suppose I have 2 matrices, right? So capital names, remember capital letters represent the name of the matrices. So I have 2 matrices, A and B. Let A, B be matrices. And of course, they have to be the same dimension, right? So let me write that, of the same dimension or size. So they're both like 2 by 4, 3 by 7, whatever they might be. same dimension, and then we're going to introduce a scalar, or let's introduce two scalars. C and D are scalars. So we got two matrices and we got two scalars. Now, if we are adding two scalars, C plus D, multiplying it by A, well, we can actually distribute the constants each to A. Okay, so that's how each of those distribute to A. If you're doing C times A and that product multiplies by a scalar D, then we simply multiply the scalars. Because they're numbers, so pretty much you can work them however you want to in any order you like when you multiply by a matrix. A scalar times the sum of two matrices, you multiply each matrix by the scalar. And in case of, let's say, C times D, two constants times matrix A, you can do C times and then do D times A. Okay, now for example, like where would you want to do something like this one? Suppose I'm doing 3 times 1/2 and my matrix is going to be 2, 4, 6, 8, something like that. Well, if you want to, I can do 3 times. Instead of doing 3 times 3/2, I can do 3 times and then do a half times matrix 2, 4, 6, 8. Because these are even numbers, the way I made them, a half times each of those makes this 1, 2, 3, 4. So you see, it just makes it easier to work with. Or my matrix could have been, let's say, 1/3, 5/3, 6/3, and well, 6/3 is too, don't want that one. Let's go 7/3 and 8/3. There are things that don't cancel. All right, and my scalars are 5 times 3. Well, instead of doing 5 times 3, we can distribute 3 to the matrix, every element of the matrix. And now I'll be working with whole numbers. You see that? That would be one such instance where this would make sense. Our job is to kind of show what's legal, what can be done, and whether you do something with it or no remains to be seen. Okay, the matrix. Suppose I have 3, 5, 2, 4. We're going to do an example of matrix, scalar multiplication of matrices. Let's make this one to be 0, 1, 3, -1. Okay, and suppose I want to do this. Suppose I want to do 3A. Well, 3A, that means you triple every element of that matrix. So that's going to be 3A. -1/2 B. Well, -1/2 B, that's going to be 0, -1/2, -3/2, and 1/2. Right? You divide every element of matrix. My negative doesn't look that impressive. There we go. You divide every element of matrix B by 2 and change the sign. Okay. What if I want to do 2A minus B? Okay, 2A minus B. Well, twice A, double up on the elements, so I get 6, 10, 4, 8. That's 2A, and then I'm going to add, actually, yeah, minus B. Remember, we're going to do addition with opposites. So I'm just going to actually add to this one. Negative of B, which is negative of that, so it's going to be 0, -1, -3, 1. That's negative of B. Now we're going to add the corresponding elements, and that will make it 6, 1, 9, 9. Right? And there you have that. Again, it's pretty straightforward. So we can do addition, subtraction that way. Remember, there is no matrix division, so don't be tempted to do it. And if you found a way to do it, let me know. But it cannot be done as of today. Now, the next operation on matrices, quite interestingly, is matrix multiplication. Okay, so let me actually do a copy paste job here of matrix multiplication template, because it's going to look nicer than if I wrote it in. And there you have it. Again, just like magic, it appears. So let's take a look at our matrix multiplication. I'm going to read this multiplication definition, and it's not the way it's kind of first time you're looking at it, it doesn't make sense, but eventually it will make sense the way it's done. But it's not your usual multiplication the way you would expect it. So let's read on the matrix multiplication here. So let's say I have two matrices A and B. Okay, so the number of column of A is m by n, and the other matrix is n by p. Okay, so here you go. I have the first one, A is m by n. The other matrix is going to be n by p. All right. Now, the way this multiplication is done is that you look at the ith row of the matrix, and this would be the jth column of the other matrix, matrix B. So the way the multiplication works is you multiply now a I1 times a b times b1j. Then we multiply ai2 by b2j, and so on and so forth. Ultimately, you multiply the element in the inth position by the element in the njth position. So that's how they multiply together. Now, for this to happen, because you need to have a matching element to multiply by, therefore that does require that the inside numbers for the dimension of the matrix, if the first one is m by n, the second one n by p, the number of columns, the columns in the first matrix should equal to the number of rows of the second matrix that you're multiplying. Okay, so that one-to-one correspondence of the elements in multiplication makes sense, and it will exist. So don't forget that then. These inside numbers must be the same. The outside numbers, in this case m and p, if you multiply AB, the size of this final matrix is going to be m by p. That is m rows and p columns. Okay, so that's what this is telling us. Now let's take a look at actually one example here. When it comes to matrix multiplication, by the way, matrix multiplication is not commutative. Multiplication of matrices is not commutative. So what does that mean? That means the order that you multiply the matrices makes a difference. So AB in general does not equal to BA. Only for special matrices that's true, not in general. So matrix multiplication is not commutative. And sometimes it's not even defined. So for example, let's say A is 3 by 4, and B, remember inside numbers must be the same, is 4 by 5. So this matrix multiplication is defined, right? The product AB will be defined, and it will be 3 by 5. Now suppose I change the order of these exactly the way they are. So B is 4 by 5 and A is 3 by 4. See, the inside numbers are different. They're not the same. So this is not defined even. It's undefined. We cannot do it. So please keep in mind, again, this one among the list of other things you have to remember. Now, let's take a look at the associative and distributive property, and then I'll show you several examples of matrix multiplication until you feel comfortable with this operation. So we're looking at now the associative and distributive property of matrices. Associative and distributive properties. So here's how it works. Suppose I have, and assuming A, B, C are such that the product is defined. So if I'm doing A times B times C, the associative property still works. You can do B times C and then do A times BC. Okay, how does the distributive property work? If I have A times B plus C, that would be A times B plus A times C. Another one, let's say I have B plus C times A, and this is going to be B times A. And this is distributive. We distribute from the left, by the way. Makes a difference. Remember, from the right or from the left, it makes a difference. But the distributive property is BA. I guess from the right, if you keep the order the same, that also makes sense. But sometimes when people do this, like distribute from the right, A times B, they just write it the way it distributes. That's what I'm afraid of. So that's what I say, distribute from the left. Okay, so we got those three things. And what else? So let me also mention that this does not equal to, if you're thinking distributive property from the right, that will make it look like this, then that's not true. That won't work. Now, let's take a look at several examples here to make you comfortable with this operation. So my first example, suppose I have a matrix. It's going to be a 2 by 3, 3, negative 4, 1, and then 5, 0, 2. Okay, so this is a 2 by 3 matrix. My other matrix is going to be a column matrix. Remember row column matrices? It's a column matrix that has 3 rows, 1 column. Make sure the inside numbers match so we can multiply them. So how is this multiplication going to go? Well, the outside numbers on the dimensions of the two matrices give you the size of the final matrix. The final matrix, the answer, the product matrix, if you will, is going to be a 2 by 1. So see, I'm preparing myself for 2 rows and 1 column. We're going to fill in the numbers in these in just a moment. Now, if I write the elements of this product matrix, that's A1, 1, A2, 1, right? Using the subscript notation. So this, in a way, tells me how I'm supposed to do this. To get the number in this position, I need to multiply the first row of A, call this matrix A, and this one B. Okay, first row of A, and the second subscript would be first column of B. So what is that telling me? First row of A, first column of B. That means I need to multiply first row of A, the elements in the first row, by the first column of B. Now, of course, B only has 1 column, but the subscript, the way I do it, it will help us with larger systems, not necessarily row or column matrices. Okay, so we're going to do that. So how is this going to work? Well, remember, we multiply each corresponding elements together. There, that's how it's going to go. That means I'm going to do 3 times negative 1, and then we're going to add to that negative 4 times 4, add to that 1 by 2. Makes negative 3, negative 16 plus 2. And the sum here is going to be negative 17. Right? So that's going to be negative 17 is the first row, first column element of the product matrix. All right. And that's how I got this number. Let's take a look at the second row, first column element of the product matrix. Remember how this goes. The first, in the subscript, the first number tells you now second row of A, and the first number in the column tells you first column of B, the other matrix. So how am I interpreting this now? This time I need to multiply the second row of matrix A, and the second row of matrix A is now this one, times it by first and only column of matrix B. Now let's do that. So I'm going to do 5 times -1 plus 0 times 4 plus 2 times 2. And that's going to be -5 plus 0 plus 4, or -1. And that's going to be the product. You see that? That's the complete multiplication. 5 times -1, 0 by 4, and 2 by 2. That's how it's going to go. It's actually pretty dynamic, right? It's very exciting to multiply matrices. Their addition, subtraction is kind of boring. Multiplication is a little more exciting. I know it's still boring, but not as boring, I should say. Exciting because there's a lot going on there. And this is, by the way, the answer is as we expected it to be, right? We expected to have a 2 by 1, and of course it turned out to be a 2 by 1. Let's take a look at another one. This example, so this time I'm going to go -3, 0, 2, 1, and then 4, 0, 2, 6. All right, and we're going to multiply this by, I'm going to go with a 2 by 2. Okay, 2 rows, 2 columns, 3 rows, 3 rows, 2 rows, 4 columns. So what do you think? Can I multiply these? Let's look at the inside numbers. A 2 by 4 times a 2 by 2. The inside numbers are not same. They're not the same, right? If they're not, therefore this multiplication, matrix multiplication, is undefined. So I'm just going to say this cannot be calculated. Again, because it doesn't meet the requirement, the inside numbers must be the same. As I try to multiply this by would be the columns of this one, I'm going to go -3 times -4, no problem. Add to it 0 times 0, no problem. But then 2, see, 2 doesn't have one to multiply with here, neither does 1. Doesn't have one to multiply by down there. 1 by what? They don't exist. So multiplication is undefined. Alrighty, and so that was easy. Let me just clean up this a little bit so it looks better. And get rid of that. And I said these numbers are not the same. Okay, let's take a look at another one. Now, one that's actually defined. This is going to be interesting. Let me do this. Let's try to multiply 1, 2, 3. Easy to remember. This is a column matrix. 3 rows, 1 column. We're going to multiply this by 3, 2, 1. Okay. Now this one is a row matrix. 1 row, 3 columns. Isn't that amazing how this is going to work out? The fact that the inside numbers for the dimension of 2 matrices are the same means multiplication is defined. So what is the product going to look like? Well, the product's going to be, it's going to be a 3 by 3, isn't it? Let me write the elements, because remember the outside numbers will be the dimension of the answer. This will be the size of the product. So I'm preparing for a 3 by 3, A1, 1, 1, 2, 1, 3, second row first, second, third, third row first, third, second, and third row, third column. Aha. And remember how we did this one. The position, actually, the position of the elements in the product matrix tells you what to do. So let's begin with first row, first column. Well, remember, that's when you multiply first row of the first matrix by first row, the element in the first row of the matrix, by the element in the first column of the second matrix. So this is going to be 1 times 3, because there's only one element there. Done with that one. A1, 2, first row, second column now. 1 by 2. A1, 3, you do 1 times 1. First row, again of the first matrix by the third column of the second. Let's look at A21. A21, so that would be the second row of the first matrix, and then each of these 1, 2, 3 will go 1, 2, 3 like that. So you got to do 2 times 3, 2 by 2, and 2 by 1. And that is how you multiply those. Now finally, to do the last row here, A31, for example, means third row of the first matrix and first column of the second matrix. So it's going to be 3 by 3. Then it's third row, second column, third row, third column. And that's how they multiply. Isn't that cool? Now we can, of course, do the arithmetic and finalize this. 1 times any number is itself. And 2 times 3, 2, 1, that would give me 6, 4, 2, doubles up on the numbers in that row. And then you triple them, 3, 6, 3, 9, 6, 3. 3 times whatever made that 9, 6, 3. And there you have it. The size of this matrix is a 3 by 3. Cool. And we are good with this product. Now let's take a look at something interesting. Another interesting product. Suppose now I'm doing, let's do the same thing. We're going to do 1, 2, 3. This time multiply by 3, 2, 1. See the one that I just did above that? It was a column times a row matrix. Now I'm multiplying a row by a column matrix. 1 row, 3 columns. 3 rows, 1 column. The inside numbers are the same. The outside numbers will be the size of the matrix. We're going to have a 1 by 1 matrix. A 1 by 1 matrix is just that, right? Has 1 row, 1 column. So how the product's going to go? First row, first column. The only row and the only column. You multiply the elements like that. So I do 1 by 3 plus 2 by 2 plus 3 by 1. And the sum's going to be 10, right? That's 3 plus 4 plus 3, that's 10. Cool. And that's the final matrix. It's a 1 by 1 matrix. Even though it's a number, by the way, we write it as a matrix, right? We don't write them like that usually. Since we're talking about matrix, might as well keep everything as a matrix. All right, got done with this part. Now, we can also, by the way, square matrices and things like that, because squaring is like multiplying the matrix by itself, right? So for example, let's say A is a 2 by 2. I have 1, 2, 3, 4. And I want to do A squared. Well, A squared is A times A, right? As long as there, that's a square, I'm going to be okay. So I'm going to be multiplying the matrix by another version of itself. 1, 1, 2, 3, 4. And the product's going to be a 2 by 2, right? First row, first column. So we go 1, 1, 2, 3. That's 7. Right? That gives me element in the first row, first column. First row, second column. So I'm going to go first row, second column elements. 1 by 2, 2 by 4. That's 10. And then we do 3 by 1, 4 by 3. That's 15. And finally, to get the second row, second column, you do 3 by 2, 4 by 4. That's 6, 16, 22. So notice when you do square of a matrix, like the one I did here, you don't square the elements of the matrix, right? We cannot square them. So A squared doesn't equal to 1 squared, 2 squared, 3 squared, 4 squared. So I wish it would work that way, but it doesn't. You actually have to write it. So if you want to do a cubed, now I have to do a squared times a, and then you go so on and so forth. All right. And I think that's pretty much all I wanted to talk about in this section. Just some basic operation with matrices is what we wanted to do with this one. So we looked at, again, some properties of matrices. We looked at addition, subtraction, multiplication. There is no division of matrices. And we looked at the associative and distributive property. We looked at the scalar multiplication with matrices as well. All right, and with that, we are done with this lecture. Thank you for watching.